the whisper of the 11th dimension, unseen geometries and the fabric of reality. To speak of the 11 dimensions is to venture beyond the comfortable confines of our perceived reality, to peer through the shimmering veil that separates the tangible from the profoundly theoretical, a journey demanding a suspension of everyday intuition and a deep embrace of mathematical elegance. We exist, undeniably, within a four-dimensional space-time continuum, three spatial dimensions charting length, width, and depth, woven inextricably with the unidirectional march of time, a concept so fundamental yet so bafflingly asymmetrical in its flow. This four-dimensional framework, formalized eloquently by Einstein's theories of special and general relativity, serves as the bedrock of classical physics, accurately describing everything from the trajectory of a celestial body orbiting a star to the bending of light around a massive galaxy cluster, a phenomenon known as gravitational lensing, where the curvature of space-time itself acts as a cosmic magnifying glass. However, as physicists push the boundaries of understanding, particularly in reconciling the smooth, geometric tapestry of general relativity with the probabilistic, quantized realm of quantum mechanics, the neat four-dimensional picture began to fray, revealing inconsistencies at extreme scales, such as the singularity within a black hole or the initial moment of the Big Bang. It is in this crucible of theoretical necessity, driven by the search for a unified field theory, a single, comprehensive equation describing all fundamental forces of nature, that the notion of extra dimensions, specifically 11 of them, emerged as a compelling, almost inevitable, mathematical consequence. The genesis of this multidimensional speculation lies most prominently within string theory, or more precisely, superstring theory, which posits that the fundamental constituents of the universe are not point-like particles, as described by the standard model of particle physics, but rather tiny, one-dimensional vibrating filaments of energy, akin to infinitesimal rubber bands. The different modes of vibration of these strings correspond to the different fundamental particles we observe, an electron vibrating in one pattern, a photon in another, and the elusive graviton, the hypothetical carrier of the gravitational force, in yet another. For the mathematical consistency of these theories, to prevent nonsensical infinities from arising in calculations, the strings cannot vibrate in just three spatial dimensions, they require a higher dimensional arena in which to oscillate. Initially, early versions of string theory necessitated 10 dimensions, 9 spatial and 1 temporal, but the subsequent unification efforts, particularly the development of M-theory in the mid-1990s, which synthesized 5 different, previously disparate versions of superstring theory, elegantly settled on a framework requiring precisely 11 dimensions in total, 10 spatial dimensions and 1 temporal dimension. These extra dimensions, the 7 beyond our familiar 3 spatial ones, are not immediately apparent to our macroscopic senses. If they exist, where are they hiding? This leads to the central conundrum of higher dimensional physics, the compactification hypothesis. The most widely accepted explanation is that these additional spatial dimensions are curled up, or compactified, into incredibly small geometrical shapes, far smaller than even the Planck length, which itself is estimated to be approximately 1.6 times 10 to the negative 35th meters. Imagine a garden hose viewed from a great distance. It appears as a one-dimensional line. Only upon closer inspection does one perceive the second, tiny, curled-up dimension, the circumference of the hose. Similarly, the proponents of string theory suggest that our familiar large dimensions are the uncompactified dimensions, while the extra dimensions are curled up so tightly, perhaps into intricate geometric structures known as Calabi-Yau manifolds, that they remain invisible and dynamically inert to the particles and fields operating on the large, low-energy scales we currently probe. The geometry of these Calabi-Yau manifolds is not arbitrary, it is mathematically rich and critically important because the precise shape and size of the compactified dimensions dictate the physical laws and constants we observe in our four-dimensional universe. This is a breathtaking implication: the electron's mass, the strength of the electromagnetic force, the cosmological constant, all the fundamental parameters that define our reality, would be emergent properties stemming directly from the topology and geometry of these hidden, microscopic dimensions. Calculations suggest that the sheer number of possible Calabi-Yau shapes is astronomically vast, perhaps on the order of 10 to the power of 500, leading to the concept of the string theory landscape, a vast sea of possible universes, each with potentially different physical laws dictated by its unique compactification scheme. Our universe, therefore, might simply be one valley within this immense landscape, defined by a specific, stable configuration of the curled-up dimensions. The 11-dimensional framework of M-theory offers a profound conceptual shift beyond just vibrating strings. M-theory introduced the concept of brands, short for membranes, which are higher-dimensional objects upon which strings can end. A zero-dimensional object is a point, a one-dimensional object is a string, a two-dimensional object is a membrane, and so on, up to the p-brane, where p denotes the number of spatial dimensions the brane occupies. In M-theory, the fundamental objects are thought to be 2 brands and 5 brands, existing within the 11-dimensional space-time. Crucially, the standard model particles, the quarks, leptons, and force carriers like photons and gluons, are often hypothesized to be excitations of open strings whose endpoints are stuck, or anchored, onto one of these large, 3-dimensional brands that constitute our observable universe. This brane-world scenario provides a compelling, though still unproven, explanation for why gravity seems so extraordinarily weak compared to the other 3 fundamental forces: the strong nuclear force, the weak nuclear force, and electromagnetism. If the particles mediating the other forces are confined to our 3-dimensional brane, their interactions are confined to that surface. However, the graviton, being a vibration of a closed string, is not required to have its ends tethered to the brane. Consequently, gravity, in this model, is free to leak, or propagate, into the higher, extra dimensions, effectively diluting its strength across the bulk spacetime in which our brane is embedded. This idea, sometimes called the ADD model, after its proponents are Carnehamd, Dimopoulos, and Dvali, suggests that gravity's weakness is merely an illusion of our limited perspective. If we could somehow probe the bulk, perhaps by achieving energies high enough to excite gravitational modes into the extra dimensions, we might observe gravity strengthening dramatically at very short distances, a phenomenon that experimental searches, such as those conducted at the Large Hadron Collider, are subtly attempting to constrain, looking for anomalous energy missing from collision events that could signify energy escaping into hidden spatial directions. The structure of these hidden dimensions fundamentally impacts causality and the very nature of physical laws. In a hypothetical world where the extra dimensions are large rather than compactified, a concept explored in models like Randall-Sundrum, the geometry is even more dramatic. In the Randall-Sundrum scenario, we reside on a 3-brane embedded in a 5-dimensional spacetime, 2 large extra spatial dimensions plus time, where the 5th dimension has an unusual warp geometry, governed by a specific metric that causes distances to be stretched or compressed depending on one's location relative to the central plane. This warping naturally explains the weakness of gravity without requiring the extra dimensions to be microscopically small, although the tension between the large extra dimension scenario and the constraints imposed by precision measurements of gravity at millimeter scales remains a vibrant area of debate. Beyond the search for direct experimental verification, the contemplation of 11 dimensions forces us to re-examine time itself. The temporal dimension, the 4th dimension in Einstein's original framework, remains stubbornly unidirectional in our experience, entropy always increasing, marks on a clock always advancing. In higher dimensional theories, the nature of time can become more complex, potentially involving cyclical models or a reinterpretation where what we perceive as the evolution of time is actually a progression along a specific path within a higher dimensional geometry. The very notion of a smooth, classical spacetime gives way to a quantum foam at the Planck scale, where spacetime itself is thought to fluctuate violently, a place where the concept of a fixed, pre-existing dimension loses meaning until the system settles into a lower energy, macroscopic configuration, our familiar for dimensions. Consider the mathematical tools required to navigate this terrain. Tensor calculus, the language of general relativity, must be extended from 4 dimensions to 11, requiring the manipulation of objects with 11 indices, a significant increase in complexity. Furthermore, the symmetry groups that govern particle interactions in the standard model, specifically SU3 times SU2 times U1, must find their ultimate embedding within a larger, more encompassing symmetry that naturally arises from the geometry of the 11-dimensional space. The discovery that the maximal possible spacetime dimensions consistent with supersymmetry, a theoretical symmetry relating fermions and bosons, is indeed 11, lent significant theoretical weight to M-theory's specific dimensional count. The implications for cosmology are staggering. If extra dimensions exist, the Big Bang might not have been an abrupt beginning from a singularity, but rather a consequence of the collision or interaction of higher dimensional objects, perhaps two brands momentarily touching, or the resonance of bulk fields settling onto our brain, initiating the expansion we call the universe. The inflationary epoch, the rapid exponential expansion immediately following the Big Bang, could be modeled as a phase transition in the geometry of the compactified space, a mechanism for smoothly dialing in the precise physical constants required for baryogenesis and structure formation. The dark energy currently accelerating the expansion of our universe, a mysterious repulsive force quantified by the cosmological constant, observed to be minuscule but non-zero, could potentially be explained as the tension or vacuum energy associated with the extra dimensions themselves, the subtle pressure exerted by the bulk spacetime onto our brain. However, the journey into these unseen realms is fraught with theoretical hurdles. The problem of moduli stabilization is paramount. If the extra dimensions exist, what locks their size and shape into the specific Calabi-Yau configuration observed today? Fluctuations in the size or shape of these compact dimensions would manifest as slow variations in fundamental constants over cosmic timescales, variations that have been rigorously searched for using astrophysical observations of ancient quasars and the decay rates of radioactive isotopes over geological time. So far, these constants appear remarkably stable, implying that the mechanisms stabilizing the moduli, the parameters defining the size and shape of the curled dimensions, must be incredibly robust, often requiring complex potential energy landscapes within string theory that trap the system into a minimum energy state corresponding to our observed constants. The elegance of the 11-dimensional picture is its promise of unification, yet its opacity remains its greatest challenge. We cannot directly observe these dimensions, and current particle accelerators, while pushing the energy frontier, are fundamentally limited by the energy required to probe distances close to the Planck scale, where these extra dimensions would exert their most noticeable influence. The Planck energy is roughly 10 to the 19th giga-electron-volts, far exceeding the current capabilities of the LHC, which operates in the range of around 10 to the 4th giga-electron-volts. Bridging this vast chasm of energy, often referred to as the hierarchy problem, the immense gap between the electroweak scale and the Planck scale, is precisely what the higher dimensions are hypothesized to explain via the gravitational leakage mechanism. Furthermore, the mathematics of EM theory itself remains incomplete. It is not fully formulated as a definitive action principle or Lagrangian, though its low energy limit is generally agreed to be 11-dimensional supergravity. The theory exists, for now, largely as a collection of dualities, mathematical equivalences showing that seemingly different physical theories operating under different dimensional setups are in fact descriptions of the same underlying physics. For instance, S-duality relates strong coupling in one theory to weak coupling in another, while T-duality relates a theory compactified on a circle of radius r to a theory compactified on a circle of radius 1 over r. A profound relationship that suggests a fundamental minimum size dictated by the structure of the theory itself. If we were to, hypothetically, possess the technology to traverse these unseen dimensions, the experience would be radically different from moving through our familiar three spatial axes. In a compactified dimension, movement would be cyclical. Traveling a certain distance in that dimension would bring you back to your starting point, analogous to walking around the circumference of the curled hose. In large extra-dimension scenarios, the geometry might be warped, meaning that moving a certain physical distance might correspond to traversing a vastly different amount of intrinsic space-time metric, leading to bizarre relativistic effects or a dramatic alteration in the perception of simultaneity if one could interact with matter existing in different regions of the bulk. The exploration of these higher dimensions is not purely abstract mathematical speculation. It is a profound scientific endeavor driven by the observation that our current best models of physics are incomplete. The Standard Model, while spectacularly successful in describing three forces and all known matter particles, omits gravity and leaves the nature of dark matter and dark energy unexplained. 11-dimensional frameworks, by providing a geometric foundation for all forces, offer a path toward a theory of everything. The dimensions are not just mathematical curiosities, they are potentially the scaffolding upon which the entirety of observable reality is built, an unseen framework whose subtle influence dictates the very constants that allow atoms to form, stars to burn, and life to emerge. The continuous search for anomalies in particle collisions, minute deviations in gravitational measurements, and correlations in the cosmic microwave background radiation represents humanity's most sophisticated attempt to feel the texture of these hidden geometries, the whisper of the 11 dimensions echoing just beyond the reach of our senses, waiting for the right key to unlock their spatial secrets. The truth, encoded within the vibrations of infinitesimal strings across 10 spatial axes, remains the ultimate frontier of physics.